Now, how can you check this? How would you verify whether or not this is true? What experiment could you do to figure out the magnetic dipole moment of a bar magnet? What would it involve? Okay, let's calculate the field strength. How would you calculate the field strength of a bar magnet? With a compass. Right, we've done this with currents, so we could do this with a compass. If you had a compass, and let's say geographic north is that way, so if you just have a compass, it's going to be pointing in that direction. And then I bring, now there's a lot of norths running around here, but I bring the magnetic north pole of the bar magnet near the compass. What's going to happen to the compass needle? It's going to deflect, and it's going to deflect that way, right? So when I bring the bar magnet nearby, it has something that looks like that, right? I could then do exactly what you've done for homework a couple times now, measure that angle, use that angle to figure out the magnetic field due to the bar magnet, and then once we have the magnetic field of the bar magnet, if we assume it's a dipole, we can say that the magnetic field of a dipole is mu naught over 4 pi 2 mu over z cubed. But measure how far away it is. I've got the field strength. I could solve for the dipole moment. Okay, and this is something you're going to do in lab. Not, let's see, next week. Yeah, I think you'll actually do this next week. And you should find, just sort of keep this number in your notes and see if you find something that's at least close to this or on the sort of same order of magnitude. So again, just showing that a very simple model, microscopic calculation leads to something that we can predict and actually measure in a simple laboratory experiment. Okay. Questions? Okay. Here's another question. You cut a bar magnet you cut a coil in half. So each new coil, so let's just think about a current carrying coil first. You cut a coil in half, each new coil has half as many turns as the original coil. What are you going to get? One coil with a north pole, one with a south pole, two weaker coils, each with a north and south end, or two coils that don't make any magnetic field when currents run through them. So yeah, you're taking a coil, you're cutting it along perpendicular to the axis, right? So here's the coil, and you cut it that way, okay? So just about everybody says, answer number 2, two weaker coils, each with a north end and the south end, right? Because if I have just two separate coils, each with the same current direction, then they're both going to be producing dipole patterns of field, right? If conventional currents going like that in each, you're going to have B pointing that way over here, B pointing that way over here, okay? So you can guess what the next question is going to be. Do the same thing with a bar magnet. You cut a bar magnet in half so that each new magnet is half as long as the original magnet. What do you think you're going to get? Okay, again, you're going to actually get two weaker bar magnets because the model is it's behaving just like a coil, right? If our model is we've got all these atoms such that the electrons are lined up and orbiting in the same direction. So there's one orbiting that way, and there's one orbiting that way, and there's one, and there's one, and there's one. It's just like having lots of current loops or lots of coils, loops, lined up in the same direction. So if you cut it in half like that, you just get a smaller number of atoms, each with those loops, those electronic current loops lined up in the same direction. So I just end up with a magnet. One has a south and north pole, and the other one has a south and north pole with magnetic field pointing away from one end and towards the other end. Okay, so it seems like the only possible pattern we can get for a situation like this is a dipole pattern. What would a single north pole look like? If we could imagine a single north pole, what would the pattern of magnetic field look like around a single north pole? It would look like a point charge. It would actually look like a point charge, right? If we could imagine this, we'd actually have a situation analogous to a point charge with electric fields, where the magnetic field is pointing all directly away from the North Pole. If you had a South Pole, the magnetic field would be pointing directly toward it, right? Well, so far as we know, this doesn't exist. No one's ever found a single isolated North Pole or a single isolated South Pole, or what's called a magnetic monopole. Yeah. And there have been people looking for them for a long time and doing particle physics experiments where they're smashing high energy particles together to see if magnetic monopoles pop out. And so one of the things that they might be looking for at the Large Hadron Collider in CERN is the presence of magnetic monopoles. But so far, no such luck. Okay. So if you find a pattern of magnetic field that looks like this, if you're doing a calculation or if you're drawing a magnetic field or something like that, you've either made a mistake or you made a discovery, right? You just won yourself the Nobel Prize, right? So keep that in mind, all right? No magnetic monopoles. Okay, couple minutes left. I just want to say real briefly something else about bar magnets. We said, so only certain types of materials seem to exhibit this behavior, right? Iron, cobalt, nickel. So what's special about them that we can't seem to produce in other metals? So ferromagnetism is what this phenomenon is called. And it's actually a pretty hot topic of research because it's a highly quantum mechanical property. It involves really knowing a lot about the quantum mechanical behavior of matter at the microscopic level. But the idea is that these electronic orbits, and really our model's a bit simple. We're talking about the orbits, but I believe it's mostly the electronic spins. So not only do electrons orbit the atom, but they have some inherent spin of their own, meaning they have some inherent angular momentum, sort of like a spinning on their own axis, if that were possible, that contributes to this dipole moment. But if you can get these microscopic dipoles lined up, as we had, you can produce a bar magnet. Well, I'm drawing arrows here that indicate the direction of these angular momentum vectors, or these dipole moments. Okay, basically it's kind of like the direction of the field due to a single dipole. And it turns out there's a tendency in iron, nickel, cobalt, certain other materials, for at short range, the spins tend to line up. The atoms tend to line up in what are called domains. And so these areas are called domains. At long range, they tend to not line up. And that is because it's energetically more favorable to have, if you can even try this, if you try to place two bar magnets next to each other and line their ends up, so north is near north and south is near south, they'll tend to repel each other, and one will flip around and they'll end up north-south, south-north. Okay, so over long range, there's a tendency for them to not line up. But for certain materials like iron, quantum mechanically, they tend to line up. Okay, so you get these domains where all the spins are lined up in different directions, but they're got sort of patches where they are aligned. And so some are pointing one way, some are pointing the other way. And so overall, in just an ordinary piece of iron, net magnetic field this produces is 0. Then you apply a magnetic field to this system due to, say, an electromagnet or a coil, and let's say the magnetic field is pointing up. So applied field. Well, you can get the domains that have their spins lined up mostly in the direction of that field to grow. And so maybe this domain grows a little bit at the expense of all the others. And maybe this domain, where it's kind of lined up in that direction, grows at the expense of the others. and the other ones kind of shrink. Okay, so maybe that one grows too. And so now, I didn't quite draw this very well, but you end up with most of the domains are kind of aligned in the same direction, and now it can actually produce a net magnetic field at a particular location. And then if you take this magnetic field away, you can, in certain circumstances, cause these domains to sort of lock in and stay that way, and then you produce the permanent bar magnet. Okay? But it's susceptible to things like temperature. If you heat things up, if you heat the bar magnet up, you cause the atoms to start vibrating around, and then the domains don't tend to line up anymore. So it's a special property of certain materials that you can get this sort of lock-in and get these domains to line up in a particular way, but it doesn't happen all the time. Okay? So you can read more about that in the textbook if you want, and next time we will start on electric circuits.